All right, everyone. Well, thank you so much for joining. Good morning, good afternoon, or good evening, depending on where you are connecting today. And welcome to this webinar regarding the blackout that happened in Spain in April. So we have two amazing speakers today, Javier Revuelta and Prantik Saha. Thank you so much for joining. Before we start, let us do a couple of housekeeping rules. And then we can start knowing a little bit more about our speakers today. So this webinar is being recorded, and it will be shared to you by email in a couple of days. So please stay tuned. If you have any questions, please use the Q&A box that you have below if you're connecting on Zoom. And if also use the chat box if you want to introduce yourself, let us know why you're here. If you remember what happened, what were you on April 29th when the blackout happened in Spain? I did not have any trouble. I don't know if someone did, but I did hear very interesting stories. And if you are connecting on YouTube, you also have a chat there that we will be checking in and out. So this session will have no presentations today. So we're going to keep it very active, and we're going to keep it a great conversation with two different points of view, different backgrounds that we will get to know. So during the entire session of the webinar, feel free to ask any questions in the Q&A box or in the chat if you are on YouTube. The duration of the webinar will be around an hour or so approximately, depending on how the questions go. And if you need anything, just write to me on the chat. Happy to assist. So without further ado, let's start meeting our speakers of the day. So we have Javier Revuelta from Afry. Javier, where were you during the blackout? Do you remember? Do you have an interesting story to tell?
Not really interesting. Working from home on the laptop, lights went out. Initially, I thought some problem in my block. I live in a building, and it took me a few, maybe 10, 15 minutes to go on the street and ask, is it just my house? No, it's everybody's. And then I started hearing rumors that this was a national blackout. And this is when I said, oops, national blackout. Okay, we're not talking minutes, we're talking many hours to a day. But yeah, not a particularly interesting story.
Yeah, so it didn't take you 5 hours to arrive home or things like that, or to pick up the kids or anything.
I had some issues then with knowing where my kids were, but
yeah,
given they were in school, I knew they wouldn't be left at school. So I was fairly calm with the situation.
yeah, you were definitely. So Javier, can you introduce yourself? Let us know where you work at, what you do.
Yeah, so I have worked in, well, I'm an electrical engineer, and I have worked in only two companies in my life. About half of my 20 years experience in the Spanish TSO, Red Eléctrica, so looking very much at system operation and system planning issues. And second half of my work life in a engineering and consultancy firm called now Afry, previously Poiri. And we do currently a lot of market modeling and regulatory work to understand the dynamics, both the energy and the euros associated to the future of energy systems.
Perfect. Well, thank you so much, Javier, to be here, and welcome. All right, next we have Prantik Saha, all coming from New York. So it's a bit early there. Good morning, Prantik. How are you doing today?
I'm doing well, Christina. Thank you. I'm very, very glad to be here. I'm honored to be here.
We're happy to have you here. So, Prantik, can you tell us a little bit about your background?
Sure. So, hi, I'm Prantik. I'm based in New York, United States. I work for Black & Veatch, which is a giant engineering, procurement, and consulting firm, construction firm with a huge consulting wing. I'm an applied physicist by training. I come from a research background in different clean energy technologies like energy storage, hydrogen, carbon capture, different types of energies, clean energy technologies. And part of my work at Black & Veatch as a consultant is working with electric and natural gas utilities to do decarbonization and resource planning for grids. And while doing those plannings, we plan for resiliency. So resiliency against, either natural calamities causing blackout or fuel shortage supply causing some other problems. So these issues are raised. So I'll be speaking based on my work, my experience in those types of projects. But a disclaimer that, I'm participating in my own capacity. So my views may or may not be Black and Beach's views overall.
All right, Prantik. Well, thank you so much for joining us. And we'll start. We do have questions prepared in advance. However, as I said, if you do have a question that is not being addressed, you have the Q&A box. So happy to use that. So we're going to start. We're going to set the tone with Javier. Let's start with you and Prantik. Whenever you feel like it, feel free to join and give us your much appreciated opinion. So, the blackout of Spain. What do we know? What do we not know? And what are we currently doing towards the next steps to follow? What is the tone right now? If you're, let's say, someone who doesn't live in Spain and doesn't know very much about it, what can you tell us?
Okay, yeah, it's a long answer, and or the answer can be long, but we'll make it short. There are several reports that share, I think, the bulk of the analysis. I mean, the data that has been used for all analysis and all reports is roughly the same. So one would expect that the analysis and conclusions should be identical, and yet they are not exactly identical. There are some elements, for some I do have some answers, for others not really. But basically what we can say, to keep it simple, is that this has been very related to voltage control and not to a lack of inertia. I think a lot of power system experts, when there is a blackout, they think, well, something must have tripped a lot of generation and frequency has fallen very quickly, and the system maybe didn't have enough inertia. Inertia is basically energy that's provided in the time frame of the milliseconds, not the seconds or the minutes, but the milliseconds. And there's been a lot of discussion on whether having a lot of renewables in the system, because they are connected to a system through power electronics, and they do not have spinning devices. Wind, yes, but the energy from wind, which is a minority, by the way, on the day of the blackout, there was a majority of PV, a bit of wind. Wind does have some inertia because it has some spinning rotor with some blades, but a lot of the energy goes first through power electronics, and it is provided to the grid through power electronics. So there was a lot of energy coming from power electronics versus synchronous spinning generators. And what I can say is a lot of the problem has not been really actually not at all related to a lack of inertia, as lots of experts said in the first 24 or 48 hours. There was enough inertia, and we can, if someone has specific questions, we can go into the numbers. But I can confirm there was enough inertia. I mean, this is a very simple check for a TSO to make a mistake on running the system without inertia. The problem has really been about voltage control. These voltage control problems, I mean, there has been, as one could expect, not one single factor, but several contributing factors with a series of cascading actions that went in the direction of increasing, well, first decrease voltage, then increase voltage. There has been an issue with voltage control, which at some point went into voltages being too high, generators disconnecting actually as they should. There is a question mark, which is not 100% clear to me, on whether some generators were meeting or not the required standards. A report says no, they weren't. Another report says yes, they were. I don't have an answer on that. I guess some technical experts, eventually at some point, they may need to go and look at the specific numbers and come up with a conclusion on whether yes or no, they were meeting some standards. To make things a bit more complicated, there are some requirements which didn't have procedures to test whether those requirements are respected, yes or no, and there is no penalty to not meeting them. So even if someone finds that, yes, this generator was not strictly meeting the required absorption or generation of reactive power to contribute to voltage control, how can it be penalized if the current regulation doesn't penalize not meeting it? So there are going to be quite some questions for more technical experts looking at specific data, for lawyers to come up with a view of whether someone not meeting a requirement that's not penalized, how can it be penalized? Should it be penalized? So basically, to summarize the problem, a set of cascading elements very related to voltage control, contribution of renewables, some generators, some synchronous generators, not clear whether they were fully meeting the requirements. Maybe yes, maybe not. Depends on which report you read. And lots of things can be done. I would finish with saying that it has really been a technical problem with many technical solutions. Some of those solutions, they are at system level, some are at generators level. I mean, at system level, I mean, things can be done, and we can comment on those by installing devices in the grid, like shunt reactors, like synchronous compensators, or like SATCOMs. Actually, a lot of these words and a lot of these elements, they will actually be implemented in the coming months. There are other things that can be done at generator level. For example, some inverters, which they are called grid following inverters, they can be in the future either be adapted, or the new ones can be grid forming inverters, typically associated to batteries that we are very likely going to develop in the next few years. So a lot of things can be done at system level, at generator level. Generator level, by the way, both synchronous generators by, for example, just keeping more spinning generators as we are currently doing. That's not ideal because we're burning fuel. So we want to integrate more renewables without the need to burn fuel. We can do things on the power electronics of future renewables, such that those voltage problems will not happen in the future, even if we keep increasing the renewable penetration. So I'm very optimistic with this blackout, at least providing quite some insights on things that we were not. I mean, we the sector we're not doing in a fully ideal way. I think lots of good things are being identified, and we now have quite a range of technical solutions. It's a matter of designing them, implementing them, choosing the most effective in terms of cost and effectiveness in controlling voltage and in contributing to inertia. Even though inertia was not a problem, it could have been, or it could be in the future. So we need to look at a range of technical problems. There are many ways to address them. So I'm very optimistic that in the next few years we will build a stronger system. Renewable penetration can keep increasing, and it's a matter of deciding which are the best solutions, activate them as quickly as possible. So lots of fun work in the sector in the coming years. I will leave it here for Prantik.
Perfect. Well, yeah, definitely. Thank you for setting the tone and explaining a little bit what has happened, what do we know. Long story short, it's a very complex answer. So there's many different ways to tackle it. So Prantik, seeing it from afar, from a different country and system, how do you see the blackout, and how can you compare it to American blackouts that's happened? I remember maybe Texas a couple of years ago, and a couple others.
Yeah, sure. First of all, I mean, I think Javier's answer was very detailed, and it was kind of very educational, I think, for the rest of the world, because I didn't know much about it. We just heard about it, and we heard that investigation is going on. So thanks to Javier for the explanation. Historically, in the United States, I think the story is a little bit different. US has seen, different parts of the US has seen a lot of blackouts in the last 30 years, and blackouts have been happening, I would say, once every like 5-6 years, actually, to be honest. Majority of the blackouts in the United States have happened mostly because of weather-related conditions. say tornadoes hit and trees fell on the transmission line, they had to be disconnected, stuff like that. In California, wildfire has caused massive disruptions. So, basically wherever the wildfire happened, the transmission system has to be shut down at that point, in those points. In the US Southwest, what we had mostly a few different reasons. So Southeast. US Southeast has a lot of flooding issues happened in Louisiana, Kentucky, and all those areas. So because of the flooding issues, again, the power systems had to shut down in those areas. In Texas, what happened was it was a very cold winter in 2021. I think, yeah, or 20, I think it was 2021. There's a very cold winter, and the temperature dropped below freezing point. In Texas, it happens in some areas, but not very regularly. And what happened was in that winter, it prolonged for a few days. The pipes froze. The pipes froze. So essentially, what in the Texas grid was not planned to handle that kind of cold temperature. So that's what caused the massive shutdown. There was also a frequency trip that happened. And in the US Northeast, we had some blackouts. I think it was back in like early 2000s. And those were caused by, actually, it was funny. Some of it was caused by software bugs, the software that control power flow systems. And some of it was caused by like lightning, I remember. So to summarize, it was a lot of, to compare with what happened in Spain and following what Javier said, is that it's the fact that some parts of the grid, when we designed the grid, they were not designed to withstand some natural phenomena that are really tough to predict, like in terms of forecasting. And that happened, and the grid couldn't take it. But the good thing is that it usually got recovered within a few days. Most of them got recovered within a few days. So that's kind of like a US perspective.
Okay. Well, thank you. Thank you, Prantik, because I just threw you out that question. So moving on to the next one. So how can we prevent blackouts versus what is known as reinforced operating mode? I don't know, Javier, if you can talk a little bit about this first, and then we can follow up, Prantik.
Yeah. So currently, so for non-Spanish residents who may not know what this reinforced mode means, I mean, this is a new name from I guess the transmission system operator or the ministry. Basically, it is about connecting out of merit order of the day-ahead market schedule, which is what we call the unconstrained market schedule. Is let's say the set of generators which are dispatched for the next day. The TSO will look at this unconstrained market schedule, and it will check whether this would lead to over or under voltages or some overloads in some lines or any other potential problem. And they will decide if this unconstrained market schedule does not have enough synchronous generators, whether they are thermal or hydro, it will decide to connect a few generators here and there in different areas of the grid, and then rebalance. So in phase one, they will solve the problem, typically connecting additional generators, and typically synchronous, and typically thermal. Okay, and then in what we call the phase two of this constraint analysis, they will rebalance generation and demand by bringing down as much generation as they increased in phase one. Typically until the 28th of April, when the market was providing a schedule with no thermal generation in it, the TSO would connect at the very least 1 gigawatt of thermal generators, typically 5 or 6 units at minimum stable generation of about 200 megawatts, which is about 50% of the maximum generation of a standard CCGT. So typically they would connect 5 or 6. In terms of gigawatts, about 1 gigawatt. And after the blackout, we can see very clearly they are connecting typically 2 to rather 3 gigawatts of synchronous generators. So they multiply by somewhere between 2 and 3 times the number of minimum generators connecting to the grid. And the TSO has not really disclosed exactly what's the new calculation. Why was it 1 gigawatt before? Why is it 3 now? But they respond to operating procedures. By the way, operating procedures is the Spanish name for the Spanish grid code. Each operating procedure is, let's say, a chapter of what internationally is called the grid code. And they are doing several calculations to ensure voltage control overloads, transient stability, several technical criteria that need to be met. And the thing is, synchronous generators, for now, they contribute to solve all potential problems. They provide voltage control because they are a synchronous generator. They provide inertia because spinning devices provide inertia. And they provide, or they contribute to something that's quite unspoken because nobody or very few people understand about this, which is potential oscillations of renewables, of PV inverters or wind inverters. They can oscillate. I mean, oscillations, they do appear in the reports. And oscillations means that these PV inverters, they did produce some oscillations which are really problematic. It's like having suddenly, how do you say in English, an arrhythmia in your heart. You know, your heartbeat, if it suddenly accelerates or reduces, this is #1 priority for the doctor. Okay, and the TSO will say, all my priorities now, they go into solving these oscillations. And some of the actions the TSO took were about very quickly reducing, actually completely canceling the oscillations and reducing the oscillations of frequency and voltage. Then they came with some actions that actually had a side effect of increasing voltage. Okay, so some of the cascading effects, they started with the oscillations, and synchronous generators, they contribute to reducing the risk of PV inverters oscillating. Okay, so basically, synchronous generation does contribute to any potential source of transient stability problem related blackout. Okay, now a lot of these things that, or a lot of the grid services that these synchronous generators are providing, and which are taking us, let's say, far from the risk of blackout. It's like we were running close from a cliff. Let's say we were running half a meter away from a cliff. We fell, we had the blackout, and now we are running 1.5 meters away from the cliff. Okay, with these additional generators online. Now the next question is, can we keep integrating renewables and not having these preventative measures of having many synchronous generators connected because they're burning fuel, they're taking away space from renewables? Can we operate the system in a way such that we go back to just having 1 gigawatt of synchronous generator or even less, but then we need to ask for all those services to be provided by something else? And the good news is renewables can, renewables and power electronics, they can provide voltage control. It's just not implemented yet, neither by regulation nor by all the technical elements to actually do so. But renewables can contribute to voltage control. Renewables can provide emulated inertia with the power electronics providing electricity into the grid in a similar way or fairly similar way than synchronous generators would. And you can also have program them in a way such that they contribute to mitigate oscillations. There's something called the POD, the power oscillation damping mode of inverters, which means that renewables, through power electronics, you can replicate the behavior of something called the power system stabilizer, which is a control loop on synchronous generators that also contribute to mitigating or to dampening oscillations of power systems. So renewables can do all the things which are now being done by the safe operating mode, which is provided by synchronous generators. So that's the good news. Now, let's say not the bad news, but the comment to this good news is that this cannot be implemented in 1 or 2 weeks. A lot of these things, they need both regulatory developments and technical developments. And some of those, they will take a few weeks or rather months. Some, I don't know, might take up to maybe 1 year or two, because procuring and designing a synchronous compensator, unless you have one in your warehouse and you can eventually bring it in 1 week, you'll have to design it. How big? It's a big spinning mass. It's an expensive element. It's in the tens of millions of euros. You need to specify, design it. You need to procure it. The supply chain, the manufacturer maybe will say, actually, even if I place this order in my order book, I'll start manufacturing it. I don't know. I'm inventing, but in 6 months, and then it will be ready in 12 months. And you still need to do some civil works in your substations. So some of these elements, they may come in the system, I think, gradually. Some will come in a matter of weeks or months, such as implementing a voltage control device from a PV plant that can adapt their systems very quickly. Some other elements, like installing a STATCOM or a synchronous compensator or a shunt reactor, they can take, I don't know, maybe up to 2 years. I'm not sure on the duration. Yeah, the good news is some elements will come. Let's say the cautious view about it is, I think the safe operating mode, which is currently about having a minimum of around 3 gigawatts of CCGTs, I think it will gradually come down as some of these elements come in between the next weeks and the next couple of years, probably.
Perfect. Well, thank you, Javier. So Prantik, what opinion do you have? How do you think we can prevent blackouts? Is there anything you would like to add?
Yeah, a few points to what I think Javier's answer was very detailed in terms of how power flows through different devices or components in the grid and what can be done at the device level to prevent those blackouts. Now, in the United States, there is an organization called North American Electric Reliability Corporation. That's the organization that enforces some measures for frequency control, frequency regulation, voltage regulations like that. So what we do usually is that, say, for example, we are considering a BESS project, right? We are designing a BESS project. What the asset owner, say an utilities or say an independent power producer, is deploying it. They are the asset owner. When they issue an RFP for an inverter or other devices, they would explicitly mention that does this inverter comply with NARC XYZ regulation that does this kind of frequency control. So there are some regulatory aspects, in the United States that are designed to prevent the blackouts at the device level in the grid. However, there are other plans that are in place too. For example, recently in the United States, we have seen, or recently, I mean like in the last 10 years or so, I should say, that we have seen that there is a push for building microgrids, at least for infrastructure, or at least for those facilities that are some kind of like critical, or that may have the ability to kind of like or have a microgrid in some way, like it's feasible. For example, a good example is Puerto Rico, right? In Puerto Rico, there was a severe, tornadoes and cyclones and lost power and everything. And for a country, for a state like Puerto Rico, a territory like Puerto Rico, you need to have the microgrid set up, right? That has been one aspect. We have seen microgrids popping up in Northeast. We have seen microgrids popping up in many US military bases. We have seen microgrids being planned in California a lot. Some of them are very at community level as well. So they are usually designed to withstand any blackout for, I would say, 10 to 15 days. 10 to 15 days is the max I saw personally. So those are some like mitigation strategies. Another, mitigation strategy that we have, it's not exactly an avoidance procedure, Christina, as you were saying, but like some sort of mitigation strategy. Like if it happens, then what to do? And it's also, you have to take it in perspective of the US, because in the US, most of the blackouts have happened because of weather events that we can't control, like tornadoes, cyclones, we can't control them, right? And transmission systems get destroyed. So what we had was when we do this resource planning for utilities, we plan for a lot of black start operations. So for example, having either, I mean, back in the days, people used to do like, gas powered plants. So the idea is that, say, for example, in Louisiana, in one village in Louisiana, transmission system got destroyed because trees fell on it because of a cyclone. And say there is a hospital nearby that needs power. So initially, the power would be turned off by relays or something. And then what it would do is that there would be some black start plants, power plants, that would go online and would provide power only to those critical facilities, like, for example, hospital would be one. Hospitals could be one. So that is in the planning stage. We plan for black start operations. Now we are doing it with batteries too, which is very good, which is clean, to mitigate those situations if an unavoidable blackout happens. So
Perfect.
hopefully I could share some perspective from another
Yeah.
angle.
Absolutely. Well, thank you for that. Next question, and then maybe we can answer some of the ones that are coming in. What are the economic implications of the blackout? What do we see has happened till this date? Javier, can you answer that?
Yes. And it's a good question because I think there's quite some confusion or some wrong preliminary assessments of the impacts. To keep it very simple, I would say for now, there is no negative impact at all, I would say, because yes, this reinforced operating mode of the system, it is connecting additional CCGTs. Round number depends on the hour and the day, but round number basically, instead of connecting 1 gigawatt, it's connecting 3. So you'd think there's 2 gigawatts less space for renewables. And yet the reason why I'm saying it has no impact is because of how the ancillary services markets work in Spain. And the thing is, we have, I explained very quickly how we have technical constraints analysis every day in 2 phases. In phase one is about solving the problem, and the way the problem is being solved is by connecting a couple of gigawatts more of CCGTs out of merit order using their bids. The system operator will plug in the schedule those generators, and well, this money is paid by consumers. So actually, there is an impact for consumers. I'll come back to that. But renewables, the day-ahead market price is exactly the same with or without the safe operating mode, because the safe operating mode, it is actually implemented after the day-ahead schedule. So no impact on the day-ahead schedule, no impact on the day-ahead prices. And then in phase 2 of this technical constraint process, which is about rebalancing the system, the TSO actually asks for bids to ramp down some generation, and it is based on bids, which means that you are only ramped down, a PV plant is only or constrained down in this phase 2 if they submit a bid which is taken by the TSO, and the bid is about giving money back to the system. But basically, to keep it simple, it is you can think of it as a remunerated process, which means if you are constrained down, you still keep exactly the same margins as if you are not. So there is no economic implication for generators. There is an economic implication, by the way, for consumers, yes, because the extra CCGTs which are connected, there is a direct pass-through of this cost. It's actually substantial, very round number, just order of magnitude. We're talking close to 2 billion euros per year of additional cost of fuel of this this safe operating mode. I mean, this is just a back of the envelope calculation. And that's just the cost of those CCGTs. So in a way, we are, let's say, in an economic hurry to change this safe operating mode with CCGTs by other measures I mentioned about implementing these grid devices such as shunt reactors and synchronous compensators and so on, because in the long run they will be much cheaper than just keep burning fuel. but the impacts are not so much for the investment landscape, but more for the for consumers. And so yes, there can be some impact not only for end user bills, but also for industrial consumers. Their end price is going to be is now a bit higher than it would be if we had not had the blackout and we didn't have to incur these let's say safe operating mode. But if you think in terms of decades, in the next few years, we will basically have had we will have had just 1 or 2 very expensive years with an increment of about 2 billion. By the way, in years when wholesale prices are decreasing because of the positive benefit of renewables and decreasing gas prices. So let's say that the downward trend of energy prices is just partly mitigated by an increase, which we expect will be transitory during 1 to 2 years. So impact, again, summarizing, an impact mostly for consumers, yes, not so much for generators. And actually, I think some of the decisions we will need to make on incentivizing storage and incentivizing these grid elements, and even the controls of power electronics of some generators, all of that I think in the medium and long run, it goes in the good positive direction of being capable of reaching higher renewable penetrations with a very low risk of blackout. So overall, I would say not at all negative implications. If you are a PV or wind, or I mean in general, or a renewable investor in Spain, it's not the blackout that should scare you at all, I would say.
Perfect. Thank you. Prantik, are you good? Should we pass on to the next question, or would you like to add something too regarding the economic implications of, well, a blackout in general, not specifically the Spanish one?
We studied the Texas case as a kind of like a case study for like future resource planning purposes.
Mm-hmm.
And I know that to restore the Texas grid overall, it took about there are various estimates on what you include in the estimates or not, but it was in a few $1 billion US dollars estimate in 2021. And eventually it got passed into the customers at some point, right? That's how the utilities will eventually do it. So I think it was like the recovery process after the blackout definitely has some kind of like economic burden, and that eventually goes to the consumers.
Perfect. Well, thank you, Prantik. Okay, well, if it's okay with everyone, let's move on to a couple of questions from the audience. So, Prantik, I'm going to start with you with one. So, to what extent can high temperatures contribute to drops in frequency and grid issues generally? It's a longer question, but I think we can start with that one for a start.
I can take this one. So temperature on frequency, I would see 0 implication. I don't see how the frequency is set by synchronous generators. And by the way, it's not only the Spanish generators contributing to frequency, but it's the whole European power system, which is synchronously connected through lots of interconnectors in AC. Even there are some interconnectors in DC. For example, there is one between Spain and France, but it actually behaves, usually most of the time, it is programmed in a way such that it behaves, I'd say, almost exactly as if it was in AC, which means that frequency is basically the same everywhere all the time. And any generator tripping or if someone's thinking about how PV can be affected by temperature, yes, but not in the time frame of the milliseconds. It's just a steady state issue. I mean, if because of temperature, the production of PV modules goes down a bit, it goes down a bit all the time, and the total national supply. I mean, this does not affect frequency. It is actually easy to forecast at the day-ahead stage or several hours ahead of real time. So temperature, I don't think it has any impact. I mean, indirectly temperatures, I don't know if someone is thinking about the French issue with nuclears, when the temperature of water, of the water for one of the cooling systems of nuclear reactors. Eventually, there can be some constraint on nuclear reactors having to ramp down a bit their production, such that the increase of temperatures from their cooling systems between the intake and the outtake of water from a river, such that this increment is not very high for purely environmental reasons. There can be some impact. I don't know if that's the direction of the question, but again, this is not a frequency issue. It's more a steady state issue, which is compensated by just turning on or turning off whatever generators are available to ramp up, whether this is hydro or other nuclears or gas, some gas power plants with slightly lower efficiency, but no impact on frequency. Sorry, and the rest of the question was how can it impact frequency?
And grid issues generally.
Yeah, I would say, well, grid issues. I mean, other impacts are the capacity, the thermal capacity of lines. It goes down a bit. Typically, the capacity of lines in the very hot months, it is a bit lower, just because again the thermal capacity, which is increased. I mean, the thermal capacity is whatever. If the air is already heating the cables a lot, it's either the carrying capacity of the line, which goes down because the higher the current and the higher the impact on temperature, because of the Joule effect basically heats with the square of the current, or also, I don't know the English name, Prantik, for so la flecha in Spanish, basically
The arrow.
No, but it's a technical name for the cables. Okay. They have a shape like this.
Like an arrow?
The inductors?
So the higher the temperature of the cable, the cables, they say dilatarse, they not melt.
They're saying here it's sagging. Let's have sagging.
Exactly. The sagging of the line, it gets closer from ground, and sometimes the limit of the power flow in a line, it can be driven by how the cables, they stretch when they are hotter, so they go closer from the ground, and there's a security distance. I mean, the impact of temperature is some lines, they can carry a bit less capacity, so the flows need to go somewhere else. You know, maybe a line, instead of being capable of carrying 1 gigawatt in summer, or when in a heat wave, it can only carry 0.9 or 0.8. But flows, when a grid is sufficiently meshed, it will not really cause a problem to the grid. It just means flows need to go somewhere else. Eventually, there could be some impacts on the dispatch of units, but no, I would say no security issue. At most, the optimal economics, they are a bit more expensive, but no technical. I don't see any technical problem associated with temperatures.
Okay, there's a clarification here, just so you know, that they were meaning temperature causing loss of generation, substations overheating, etc., which indirectly might lead to a drop in frequency.
But drop in frequency only happens when unexpected events happen in let's say the time frame of milliseconds or seconds. But as long as temperature has an impact, which is, let's say, in steady state, everything can be planned for. So it's frequency problems in frequency. They deal with very short-term unexpected events, not with it's very hot and therefore a transformer or a line cannot carry enough capacity and there's a problem in frequency. Generation and demand is always exactly the same, such that frequency is extremely close to 50 hertz. If there is any fluctuation in frequency, it's not at all driven by temperature changes. It's driven by random events and lots of automatic controls on automatic controls on whether it is in synchronous generators or non-synchronous generators. There's always enough in the power system such that they can respond fast enough. And I don't see how temperature can affect any of these very short-term events.
Okay, perfect. Thank you. Prantik, do you have anything you would like to add, or can we move on to the next?
I agree with what the way Javier explained. The temperature doesn't have any direct implication on frequency, just from the physics-based analysis, right? It may have some impact from, like, when the temperature is high, the generation capacity, goes down. That's one. The other thing is that also the load goes up, the demand goes up, right? It's because everyone is using air conditioners and stuff like that. So because of that reason, what we saw in the United States, I personally don't know of any frequency problem, like not as a direct implication, but like some kind of, third or fourth order implication. But what I did see is load shedding. So planned blackouts, and it happened in California. You guys can probably Google heat wave caused blackouts in California. It's very common. They are just shut down because the load increases, the demand increases so much that the supply cannot compensate it. So I'm not sure if frequency regulation is a cause. I don't think, I haven't heard of any personally, but yeah, there is an implication at the grid scale, this load shedding.
Okay, thank you. All right, next question from the audience. So, Prantik, let's start with you for a change. Which is your perspective on how storage systems, BESS, could support emergencies, such as a blackout, for example?
Yeah, so what we have seen is that, not getting into too much of the technical detail, which I'm not an expert of, like from the power flow analysis standpoint, transient or static, is that we have been planning. So again, this is from the US perspective, so it may not be global, right? Different countries may have different strategies. So in the United States, while doing resource planning for electric utilities, what we plan for is enough capacity reserve for black start operation. So it could be a battery storage system. So the idea would be the following. Say a scenario would be the following. Say we are thinking about Texas. There was some kind of a storm. Say one part of the transmission line had to got shut down because the trees fell on the lines and stuff like that, right? And now say there are hospitals in the area that got disconnected. So there is a blackout in that area. It might not be the whole thing, but maybe in that area. The idea is that to have, say, for example, have BESS plants, battery energy storage plants, sitting at least, so what we recommend is sitting at least at like 50% of depth of discharge, or like the capacity, so that whenever so they'll be like always ready at 50%. So they cannot be discharged lower than 50%. So in those situations where you need critical power, then those battery energy systems would provide the power to those facilities. And I believe they probably plan with grid forming inverters. I'm not 100% sure about that. But so we plan to answer your question, black start operation is one way we plan to deploy battery energy storage system for such incidents. The other is obviously microgrid. Having if you want to have a microgrid, you need a renewable power generation asset, and obviously you need a storage asset, and you also need fuels for emergency purposes. So, storage in microgrid is very simple to understand. I don't think I need to explain it to anyone, but that's another strategy.
Perfect. Javier, is there anything you would like to add to this question about BESS?
Yes. So I think here there is some confusion on how just adding batteries will prevent blackouts. And I think that's not necessarily the case. I mean, batteries are definitely required in Spain for lots of reasons. And if we want to integrate lots of renewables when we have a surplus and use them at night when there is no sun or no wind, we definitely need a lot of batteries. I mean, there's no doubt about that. Now, the issue is this specific blackout, it was not caused because we didn't have, because we were having renewable curtailments. Again, it was driven by voltage control and behavior of the power system in let's say in the milliseconds time frames, because these oscillations, for example, they have nothing to do with a shortage of storage. So while storage is necessary, for example, if you think of 28th April when we had the blackout, if we had maybe let's say, I don't know, 3 or 5 gigawatts of additional batteries. And as a consequence of that, we could be injecting in the system another 3 or 5 gigawatts of PV, because the load would have been higher by the amount of additional batteries. We would have had eventually exactly the same problem. So because actually we would have a higher renewable penetration, the same problem with voltage control, the same problem with oscillations, or even higher. So just adding storage as the only solution with the current type of inverters we have does not solve the problem. The way in which batteries can contribute is, well, first to integrate renewables, but that's a very different problem from preventing blackouts. And a lot of the solution will deal with, are the inverters of those batteries, are they grid forming or are they grid following? If they are grid forming, they can contribute to an inertial response. By the way, I have some posts there, or there are some good comments on LinkedIn. You can contact me and I'll point you in which conversations are really interesting with people from the TSO, from Red Eléctrica, who provide very good insights on the grid following and grid forming issues. But you can actually have an inertial response from inverters, whether they are grid following or grid forming. There's also confusion with people thinking that only grid forming batteries, or sorry, grid forming inverters can provide an inertial response. Actually, grid following, they can also provide an inertial response. In one case, it will be called synthetic. In another case, it will be called emulated. And there are some very technical details why synthetic and emulated are not exactly the same thing. But the point is, renewables or batteries with the programming of inverters, you can actually provide an inertial response. And so again, it's not because you bring a battery that you prevent the blackout. It is because the battery comes with an inverter, which is programmed in a way which has specifications such that they contribute to voltage control and inertial response. And actually, if the problem is, for example, is simply voltage control, you don't need an inertial response. So you can have grid following batteries, or even grid following PV without a battery that's contributing to voltage control. And we had a successful, as they call it, a regulatory sandbox in Spain, where renewables were contributing to voltage control, and they don't have batteries and they don't have grid forming inverters. So we've had simple PV or simple wind, I mean, the current technology that's been contributing to voltage control. Now, this lasted just a few, I can remember if a few weeks or a few months. But this is just to say that you can solve the technical problems associated to voltage control without batteries. And vice versa, you can have batteries not contributing to solve the problems. So don't confuse batteries are good and necessary in the system with batteries, regardless of their design, will solve the specific problem we had, which caused the blackout on April 28th. So batteries are good, yes, but depends, preventing the blackout depends on what type of inverters they bring. And also they're not the only solution. So I think just people are getting confused, and they're saying batteries and renewables will solve all the problems. Well, it depends how you design things. But again, the technical answers to preventing blackouts, they take much longer than just you throw a battery in the system and that's it. No, that's not at all the case.
Perfect. Okay, well, thank you. So next question. I think this might be the last one, or almost the last one. So I know you mentioned that it was important, Javier, to talk a little bit about nuclear. So my question is there any impact on the nuclear closure calendar? What about the negotiations?
So all of this is really behind the scenes. There's really no public information on that. But my perception, based on conversations here and there, is that I think the blackout is contributing to add arguments in favor of the extension of nuclears. And it's because, being very pragmatic, a lot of the elements in the National Energy and Climate Plan, I think everyone will agree that a lot of these elements will not materialize, at least in time, not by 2030, which means that making closure decisions on nuclears, assuming that everything in the NECP will go forward, is a bad idea. And I think there is quite some consensus that we cannot rely on all the CSP, the concentrating solar that's planned in that NECP is just unrealistic. The volume of batteries we can discuss, I think it is also unrealistic, although there are enough projects to get there. I don't think the economics will take us there. And even if a lot of batteries come, they will not be grid forming. They will not have grid forming specifications because they will get built before a lot of the regulatory elements required to bring grid forming inverters, they will just not come on time. We'll have a grid forming specifications in 2 to 3 years time, and even that's just the beginning of having let's say a set of inverters with grid forming capabilities. So I think there were some arguments in favor of the extension, some arguments against, and this is just adding arguments in favor. Now, whether we now have enough, whether Spain has enough arguments to keep them online or not, I don't think it is a clear yes. My personal perception, and regardless of what I think is a good or a bad idea, I have no problem saying that on a personal level, I think it is a risky decision to get rid of nuclears, at least today. Today in the next couple of years, regardless of what I think is good or bad. What I think will happen is I think there are slightly more than 50% chances that there is an extension, a last minute extension of Almaraz 1 and 2 until 2030. But it's not at all guaranteed. So we're somewhere between 40 and 60% chances in my very subjective and personal view, which means maybe yes, maybe no. I tend to think that this blackout has contributed to go a bit above 50%. So I'm more inclined in favor of there will be an extension to be agreed between now and end of the year, but it is not at all guaranteed. So
we will see. All right. Thank you. Prantik, do you have any take you would like to share on nuclear in general?
So is the question on like nuclear related to blackouts or nuclear in general?
I would say related to blackout for the sake of, but the floor is
So
yours.
I'm not sure about Europe's perspective or Spain's perspective on that particularly. From the US, there has been first of all, if you want to plan an energy system, a grid system, to avoid blackouts as much as possible, you don't need nuclear, right? There are many other ways of doing that. The second thing is that, can nuclear help in a blackout? Yes, it has got a lot of inertia. Like if it's a 300, 400, 700, 800 megawatt generation system, it has got a lot of inertia. So by virtue of that, definitely it can provide inertia to frequency changes and all those things. Now, so the question comes now, like, does it make sense? In some way, yes. So in the last 20 years, only one nuclear project got sanctioned in the United States. It is mostly driven by the fact that nuclear projects require a lot of regulatory issues to go through because of safety, reliability, and all those things. And also it takes a lot of time for construction. So there is just like a general move away from like large reactors. For data center applications, we have seen companies expressing interest in small modular reactors that could be anywhere from like 10, 20 megawatt to I have seen up to 300 megawatt. If they come online, obviously they can probably provide some inertia just related to the blackouts in general. But in the United States, I don't see a large nuclear getting planned anytime soon. Maybe other than like SMRs, small modular reactors. And fusion is obviously a long way from now, from getting commercialized. So we are probably not talking about fusion yet.
Perfect. Well, I think our time is up. Prantik, you just stopped on the spot. So perfect timing. So I wanted to thank you both for a really excellent presentation, for clarifying a lot of different things. I know that there's tons of questions that we haven't answered. However, we will send you the questions during this week, and the recording will be shared with everyone. So I wanted to thank everyone for being here and making those really good questions. We hope to see everyone very, very soon, and y'all have a great day. Thank you, everyone.
Bye-bye.
Thank you, everyone. Don't panic if there is blackout.
Bye-bye.
Bye.
Thank you, guys. It was a pleasure.